Hi, my name is Tessa Hazard. I am in your class and I'm going to be going over quiz 5. First thing first, I'm not going to try to explicitly give any of the answers. I'm basically going to work through things how I work through them. I'm going to read through each question, classify it, and group it how I need to sort of get everything out on paper and then show you how I approach a solution and also tell you where things are in the textbook. Or in Christine's notes, I've actually never used a textbook to be able to find information on that in case you're saying, oh, this is an area where I feel like I'm struggling in. So let's begin. The first question says, how to synthesize N-ethyl butanamide from butanoic acid without using high temperature. So the first thing that I'm going to do here is I'm going to draw what I have. I know it's going to start with butanoic acid. So 1, 2, 3, 4, 1, 2, 3, 4. I always double count my carbons to make sure that they're right. Butanoic acid. And then the other side of this page, I'm going to have N-ethyl, what was it? Yeah, butanamide. 1, 2, 3, 1, 2, 3, 4. O N E T H. Okay, so here is my N-ethyl butanamide. 1, 2, 3, 4. My number of carbons are right. But is 4, and that ethyl is the substituent that is on the nitrogen of the amide. I wrote the ethyl as ET, but if you would like to, you can write CH2, CH3. It is whatever you prefer. On the other side of this here, we do this backwards, yes, we have butanoic acid. So the question specifies not to use high temperature, but I do, when I'm going over quizzes, like to remember how to do it if I did have high temperature. So if we did have high temperature, and we're thinking well over 150 degrees, because what we're wanting to happen is a condensation. We want water to leave. We would be using exactly what we want to connect to the carboxylic acid. So acid and an amine, we just connect them. It would originally form a salt, but we get it really hot, so we're able to form that. So I'm going to write one at the top here. That is the incorrect answer, but it is still an answer because I think it's important to remember how to do this in a different situation. So I'm going to say 150 degree Celsius heat, and I would just use NH, which is just ethylamine. And that would be the incorrect way to do it, but a way to get the correct product. So thinking about what are my options if I can't use heat, we start out with a carboxylic acid, so that might be a first hint that we need to turn that into a carboxylic acid derivative, because then we can make it jump down a chain and maybe use that to kind of convert it into an amide. So the first thing I think that we could do is thionyl chloride, which is SOCl2, and that is going to turn the carboxylic acid, the butanoic acid, 1, 2, 3, 4, O, it's going to replace the OH with a Cl. So I think we get butanoyl chloride. I think that's how you name acid chlorides. And then what you can do with acid chlorides without using heat is acylation of amines. And acylation of amines was chapter 19. I'm going to write this here. What amine, I'm not going to write, I can't write the amine. But, so you have your acid chloride, and then all you're going to be needing to do is you're going to take this off, and you're going to want to attach this. So what amine could you use that only has an ethyl as a substituent? That's going to be your hint as to like where you can get the parts for this reaction from. And then that's it for number 1. So the second question has a whole bunch of reactions in it. The first one is, sorry, I've got cats and they're like over here loud. The first one is asking about a cyclic ester. So I'm just going to go ahead and write that down. I like to dump all of the information that I have when I read problems onto the paper as I read them. On the ACS, you're not going to be allowed to write on the actual ACS, of course, but you will have as much scrap paper as you need, one piece of scrap paper at a time. So if I recognize a part of a question, I want to info dump about that thing as fast as I can so that I can reference that later in the question. So it's a cyclic ester. Then I'm going to look at what our things that we're reacting with is, which is NaOH, aqueous, and heat. So when you see an aqueous base and heat, the first thing that you should think is that is base hydrolysis. That's it, that's base hydrolysis. So hydrolysis of a base, in a base of an ester, we saw as saponification in the previous chapter. I don't remember exactly what chapter it was. It might have been 17, but don't quote me on that. Either way, we saw it with triglycerides, where we reacted them and we got the carboxylate, which was that polar head, and then we got the non-fat, the non-polar tail. So there's no steps that follow this. So if we treated this like we did a triglyceride, it's just going to do the exact same thing. We're just going to cut this bad boy on the oxygen next to, between the oxygen and the carbon, next to the carbonyl. That's where you're going to cut it. That way, when you have the product that forms from this, it's just going to break open, and it's going to have 1, 2, 3, 4, 5, 6. So it's going to have 6 carbons, but that terminal first carbon is going to have a negative oxygen on it, and so it's going to be a hexanoate. And then if you want to, you can always write, when you write your product, you can say it's Na plus and then minus that, but remember that this is the main thing that you're looking for. Yeah, that's it. So that is number 1 for part 2. And I'm actually going to go through and I'm going to number these. 3, 4, 5, 6. Okay. We've numbered them so that I can go and reference them, just so you can see what I did. I just put numbers along the edge there, because he just put all of these under number 2, and that's not very helpful for referencing them in this video. So when I see number 2 in this, my first thought is going to be, I can't think with it as a bunch of letters and numbers. I'm going to turn this into a line drawing. So CH3, CH2, CO, O, CH2, CH3. I'm going to double check this. 1, 2, CH2, CH2, C, 1, CH2, CH2. Okay. So I've turned this one right here into its line drawing form so that I can easily see what's happening. The next part of this is what my first set of reactants are, and that is ethanol and its sodium ethoxide. When you see these two together, we saw these mostly grouped together in the most recent chapter, 22, on enolates, and that was like the aldol condensation and aldol reactions, and the Claisen, and what we haven't gotten to yet, which is the Michael, I don't know, some dude's name, but we're gonna get to that later. So, yes. What I'm going to do now is I'm going to say what I'm looking for when I have those two reactants combined is an alpha hydrogen, which is extremely acidic. And when I say alpha, I mean it's next to a carbonyl. So here are my carbonyls. I'm just going to circle them right here are my carbonyls. Where are my possible alpha hydrogens? Would be, well, if I look at this one here, there's none here because that is just a tert butyl on the end and there's no hydrogen on that. So it's definitely not going to be that guy. But there are 2 hydrogens here. So I'm going to choose one of these to react with the negative right here. It's going to go over and grab this, and I'm going to form my first enolate. So I'm going to go ahead and draw that enolate out, erasing what I just drew. Okay, I'm going to make sure I draw that negative charge in red so you can see what I'm referencing the entire time that I'm talking about it. Okay, and okay, that's all right. So here is my enolate that I have formed. Now, he's going to go over, and if you remember, nucleophiles are nucleophiles because in the nucleus there's protons, there's positively charged protons. They are looking for them. And this right here, this carbonyl, has a partial positive charge. So we have a mixed reaction going on here. This is going to come in, this is going to attack, and then when we have an ester involved, what's going to end up happening is this is going to jump over. He's basically going to come right back down, and you're going to have him leave as leaving group. When you have the OR from an ester leave as a leaving group, what you might notice in this particular example is when you neutralize that byproduct, you're going to have HOCH2CH3, which is just more of this product right here. So you're just forming more of the solvent that it's in, which kind of makes it really great in terms of a reaction, like what you're balancing it with. So I'm going to, I don't think I need to draw the product. I mean, I don't want to draw the product, but I need to make sure that there's no second thing happening. Alpha proton goes in, goes bump off. Okay, yep. So that's a Klein condensation, and just make sure that you count your number of carbons when you're drawing this. Make sure that you don't lose a carbon when you're connecting those products, because that's a mistake that can really easily happen. Moving on to number 3. Oh, also for number 2, for the H+, you just see that with Klein reactions. Just know that you're going to have a neutralized final product. It's not going to have a charge on it, but you shouldn't have that anyways. So for number 3, we have a keto ester. I'm just going to go ahead and write that down just to get the information out of my brain so I don't have to worry about it later. Keto ester. Remember, when I say number 3, I'm referring to the third question under number 2. So I'm going to go ahead and name this. This is ethyl because that's the substituent that's on that oxygen on the ester. So this is ethyl, and then it's going to be 1, 2, 3, oxo, 1, 2, 3, 4, 5, 6, hexanoate. I think that it is helpful practice to just kind of name things when you can. So the first thing that we have that you can notice actually is that this guy has a beta dicarbonyl. I'm going to just draw those 2 hydrogens in blue so you see these special hydrogens that I'm showing you. They are particularly acidic. And then if we go and move on to the reactants, we have 2 equivalents. Maybe that could mean that this is going to do a set of reactions. So the first thing that I'm doing again, I'm going to go over here. I'm going to take one of these. I'm going to take the negative charge of this oxygen. I'm going to go over I'm going to grab one of those hydrogens, and then I'm going to draw the enolate that that's going to form. 1, 2, O, 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 C, H. Instead of writing OCH2CH3, I'm going to write OET. Just understand that that ET is signifying that it is an ethyl. I don't know if my camera looks like it's blurry to anybody else. I mean, I'm not on Zoom, but hopefully, I don't know. Okay, whatever, hopefully it goes away. We have our enolate now. I'm going to go ahead and like draw that hydrogen back in blue, just so you know that it's there still, because we don't want to lose it, because we are going to do a couple series of reactions. So here is our new enolate. Enolates are able to behave as great nucleophiles. Again, it's got a negative charge, it is seeking a positive charge, it is nucleus seeking, it is a nucleophile. So I'm going to go and draw what is listed as number 2, which is BrCH2CH2CH2Br, which is 1,3-dibromopropane. My excellent peanut, yes, propane. So I'm going to go and draw that, and it's going to do an SN2 reaction. Remember that if there was any sort of stereochemistry here, that would be flipped, because we're doing a backside attack. So Br2, Br2, oops, I don't know why I'm saying Br2, it's BrCH2CH2, CH2. Let me just redo this. BrCH2CH2CH2, Br. Okay, got it this time. This guy, I'm going to draw him going in here. He's going to attack, oops, attack here, kick this guy off, and connect right there. And then I'm going to draw that product. And remember, we had 3 carbons with the bromine on the end, so I'm going to make sure I get all 3 of those carbons. 1, 2, 3, and the bromine on the end. And then we have this. Now we are still in basic conditions. We still have another hydrogen on that beta dicarbonyl position. So let's just take that same sodium from step 1. I'm going to do it so you can see it. Let's take the same sodium here, and let's draw it over again. It's going to go and do this. Grab this, and it's going to form an enolate again, okay? So I'm going to draw the enolate one more time. R. Okay, and then I'm going to draw it in red, just so you see the carbon that negative charge is on. Okay, bam. Now notice that there was 2 equivalents of the sodium methoxide, but there were not 2 equivalents of the alkyl halide, that 1,3-dibromopropane. But right there, we do have another bromine that we can just go and kick off doing this, forming a 4-membered ring, okay? So I'm going to go and I'm going to draw that 4-membered ring. We're doing an intramolecular attack here. And then we have one more step left in the problem. I mean, it's a couple more steps technically, but one more experimental step. So this is where we are at this point in the question. And then we have H3O plus and heat. We are going to hydrolyze the ester. Ester is a carboxylic acid derivative. Hydrolyzing it will give you back that carboxylic acid. So let's just go ahead and do that. We know this is just going to turn, oops, I forgot to do my eraser. We just know this is going to turn into an OH, right? And then what's really easy about this, we see this in chapter 22, decarboxylation. It happens when you have a carboxylic acid right here that is alpha beta. Here's a beta carbonyl to that carboxylic acid. So we are in a condition where we can decarboxylate, right? Here's the carboxylic acid carbon, alpha, beta. Basically, what this means, if you haven't gone through yet, we're just going to take this guy, and we're just going to remove him. This hydrogen is just going to go right where this is, and we're just going to remove all of this. We don't even need our hydrogens in line drawings, so this is going to end up being what your final product is. And there's actually a kind of a mini step that's in there where you have an enol, which is a vinyl alcohol, but it's just it's like basically the double bond's going to be here, and it's going to be an alcohol, but that's going to tautomerize and go right back to its keto form because it's really unstable as a vinyl alcohol. So that's what we're going to get for 3. For number 4, we have, first, looking at the product, a sort of conjugated system, right? I have a pi bond, pi cloud, I guess I could draw it like this, pi cloud, right? That's probably important. It is obviously a characteristic that sort of defines a lot of behavior for it. So I'm just going to go ahead and I'm going to write down that we have a partially conjugated system. That might be important later, and I don't want to forget that. So conjugated system. The first thing that we're reacting with is CH3 to CH. That groups together twice, so it's 2-isopropyl CuLi. We can think of this as LiCuR2, R designating those isopropyl, those alkyl groups. And if you remember the first time that we saw LiCuR2 was in chapter 18, I believe. Chapter 18, it was replacing the chlorine in an acid chloride with an R group, and it just did it once, unlike the Grignard, which adds twice to the acid chloride. So we saw it as like a special Grignard. We actually have not gone over this in class yet, but this will be what I call William Michael, some male name. This is Michael edition. This is in chapter 22, and it is conjugated addition. Basically, you see CuLiR2, it's in ethanol, I couldn't remember for some reason. It's just going to basically get rid of this and plop that R group right there. I'm going to not draw that final product for you because I don't want it actually to be cheating or something, but just know that's what it's going to do. And it's actually super simple, and it's not too much to have to worry about. It's not like where are these pieces coming from. It's just like take that alkene and the position away from that conjugated side, just put the R group there. It's not too crazy. The second one that we have for number 4 and number 2 is a Grignard. So we have a cyclic ketone. Grignards just attack the carbonyl that is at the base of that ketone, right? Because Grignards are a mega base. That carbonyl, it's partially positive, so it's just going to go in there and plop those hydrogens on, and then you see it's going to be followed by this. So we're going to have what's going to be, whatever this is going to be OH, and whatever the Grignard R group is. And it's not going to be too crazy, but that's not a double bond anymore. So hopefully that makes sense. Grignards were chapter 10, if you are having trouble with them. And there's also a really great video if you're struggling with them by the Organic Chemistry Tutor and by Khan Academy. I think those are sent somewhere earlier in the Discord that you can reference if you need to. I would really recommend them because it like makes a chart for Grignard on an aldehyde, ketone. It looked like there was somebody in the background there for a second. That was so scary. It's just my hoodie. Okay. Yes. So moving on to what is denoted as number 5, we have an anhydride here. The first time that we saw an anhydride, it was maleic anhydride, and we were using it in a Diels-Alder reaction, I think, to get this product. Just because, I don't know if you remembered, those oxygens were both like really great carbonyls with partial positives on them, so it made it a really good dienophile to like donate electrons. So maybe it was withdraw. I don't know if my term is right, but it made it a great dienophile. But what we have here, I'm just going to write it down, anhydride. Anhydrides are acid derivatives. So acid derivative chemistry, we're going to chapter 21 here. And what are we reacting it with? A primary amine. We can name that amine, so I'm going to go ahead and do that. That is 1, 2, 3. That is propylamine. That is super easy. And there is pyridine here, which you see that used as a solvent or in reactions because it is like a base that is not really too reactive, but it's going to be good at sort of just soaking up extra protons. So when you have anhydrides and you have amines, your acid derivative reactivity list you need to have memorized for the ACS. Whatever you have to do to memorize it, do it. Something. This is going to be important that you are able to do this. So the anhydride and the amine, there's only one equivalent of it. You can choose either side of the anhydride because it is a symmetrical molecule, but you're basically just going to pop that guy off. I need to be showing you what I'm doing. Sorry. You're basically going to be breaking this open. I'm going to go ahead and draw that for you. Okay, do not lose this oxygen, okay? He is still there. And you're going to be putting whatever that amine is there. If it was a secondary amine, you would have 2 R groups there. If it was a tertiary amine, this reaction would not work. If it is a primary amine, you're going to have one of those R groups and a hydrogen. And if it was ammonia, you're going to have 2 hydrogens. And now, this could technically go in here like this. However, that is maybe not necessary to happen for this reaction. It is in pyridine, and it can just be fine, I think, being left here. So I think that's where you're supposed to leave this reaction off, but I'm not 1000% sure. It is your quiz. You can figure it out on your own, but I'm going to leave mine around right there, just with the proper amine drawn in. Moving on to number 6, which is the last one on page 1 of the quiz. We have 1-hexanol. I'm going to go ahead and draw that out. HO. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1-hexanol. And then NaCr2O7 is chromic acid. So chapter 11, we had oxidation of alcohols. I'm going to make a chart for you really quickly. This chart is available in Christine's notes for chapter 11, but chromic acid did the same thing as another thing that we had. So chromic it did the same thing as KMNO4, 2 alcohols. So we have a primary alcohol or secondary alcohol. And it's like in this little chart with the 2 other really good oxidative agents that we have are PCC and Swern. Okay, so this is like a good chart to have. This 1 and 2 are designating alcohols. If you react any of these oxidative agents on a second degree alcohol, you're going to get a ketone, okay? So, ketone, we're going to fill in the bottom part of this chart. If you are using PCC or Swern, you are going to get an aldehyde. Aldehyde, I'm just going to write ald. PCC has 3 letters. Aldehyde, shortened to ald, ALD, has 3 letters. Those guys go together. But if it was chromic acid or KMNO4, you got RCOOH, which I hope you recognize as a carboxylic acid. So what we have here is a primary alcohol and something that's going to turn it into a carboxylic acid. So we're going to take this bad boy, and then we're just going to, there was a carbon here. No, there wasn't. Yeah, okay. Remember, this is where the carbon is. Don't make that mistake. I should be able to just, like, do that, right? 1, 2, 3, 4, 5, 6. Yep, okay. Then you have hexanoic acid, and then carboxylic acid plus an alcohol is Fischer esterification. So you're going to form an ester with whatever the R group is on the alcohol is going to replace the H group on this. So that R group is going to go right here. And that's it. That is the question 6 on page 1. I'm going to take a break and upload this. I'll come back later.